you about, one-to-one and onto for linear transformations. All right, let's take a stab. Let's take a stab at trying to understand those questions. So do you guys remember from pre-calculus what did one-to-one mean and what does onto mean? We don't talk about onto as much in like pre-calculus for sure, right? Maybe not at all. But let me just remind you. And this may not be a reminder. It's totally possible this is the first time you're ever hearing about these things. I could see that happening, especially with COVID and everything, right? There's no telling what's been done to you guys, So, like definition, T is one-to-one, and I will usually call this injective, left to my devices. If T of x equals to T of y, implies x equals to y. And this is, for any pair x comma y in the domain of T. All right, that's what one-to-one means. Now, for T, say a mapping from Rn to Rm, which is our context, right? We say T is onto or surjective if T of Rn, right, which is equal to T of x, such that x is an element of Rn, if that is itself equal to Rm. In other words, the range of T is equal to Rm is another way you could say that. So it's an onto map if it covers the entire possible outputs for the function, right? So there's the question of whether or not a linear map is one-to-one or onto is actually very easy. It's actually a very easy question. So like on the next test, when I ask you, is this linear transformation one-to-one or onto, you shouldn't like run away from that question in disgust. You should be like, oh, this is just that. This is easy. Because all you have to do is look at the standard matrix. All right. So like let's work it out. So for number, let me call this 1 and 2. So think about this. T of x equal to T of y means that T of x minus y is equal to 0, right? So, but of course that's the standard matrix of T times x minus y is equal to 0, right? So we need this to somehow imply that x minus y is equal to 0, right? That's what we need. See, if the only thing in the kernel, excuse me, my bad, my Math 320 was showing, if the only thing in the null space is 0, that's what we want. So remember, this means that x minus y is an element of what we call the null space. Remember that? Null space of T. If there's something in the null space which is not 0, that's a problem. Do you see why? So like basically here's the theorem. Let me just write it out. T is one-to-one if and only if the null space of the standard matrix of T is just 0. There it is. That's it. That's all you got to know. But you know how to calculate null space. Not a big deal, right? Let's work this out. Suppose we have T of x, y, z equals to x plus z and y plus z. All right, that'll do it. So my matrix is what? One, 0, 1, and 0, 1, 1. Yeah? Do you guys agree or disagree? So this, of course, is the standard matrix of T. And so what's the null space of T look like? We're talking about x, y, z such that what? We would want x plus z equals to 0 and y plus z equals to 0. So can you write the basis for the null space? Minus z minus z such that z is real. In other words, the null space here is the span of -1, -1, 1. Now, we didn't need to do all that for this example. We didn't need to do all that, right? Actually, all you have to do is find one vector, just one, that maps to 0 and yet is not 0. Once you've found that, you've shown that you've shown that the null space is non-zero, right? This obviously shows that the null space is not equal to 0, right? Therefore, this function is not one-to-one. Let me make it more precise. Like explicitly, just to convince you, I hope, if we look at T of, let's say, well, -1, -1, 1, we get 0, right? It's called one-to-one map because there's only one output that goes to that, one input that goes to that one output, right? What two inputs both go to that? Can you guys give me T of something else that also goes to 0, 0? There's infinitely many choices to put here. May I recommend 0? Okay? So therefore T not one-to-one. All right, so that's how to judge whether or not a mapping is one-to-one. We simply have to look at the standard matrix, and if the null space of that matrix is non-zero, it's not one-to-one. If the null space of the matrix is 0, it is one-to-one. It's an injective map. Simple as that. How about question number 2, onto? How do we judge that by the standard matrix? So the question is, let's look at it. I was like, did I ever move the camera? I did, okay. So you guys, look at the equation that we have to solve. Let's think about this, right? We're trying to solve T of x. Basically, we're trying to solve, we need to be able to solve T of x equals to y for any y in Rm, right? What does that mean? Like if you translate that, we've got a standard matrix of T times x is equal to y. We have to be able to solve that for any y, right? So in other words, we need the reduced to echelon form of the standard matrix of T, slapping y on the end here. Yeah? What's it have to be equal to? Context here, the standard matrix of T is m by n. It's an m by n matrix, okay? We have m rows. What do those first rows have to be if this can solve any possible y? It must be, by the theory of linear equations that went over at the start of the semester, that has to be, 1, 1, da da da, 1, right? In other words, the m by m identity matrix with, I don't know what goes over here, whatever goes over here, let's call it star, Doesn't matter. I mean, it matters. It's exactly what you need to put into t in order to get to y. Fair enough, but this is the condition. We simply need that. In short, the theorem is t is onto if and only if the rank of the standard matrix of T is equal to M. That is another way of saying we have M linearly we have M pivot columns, right? M pivot columns. So my example here at the bottom of the board, what example was this? 4? I can't remember. Let's call it 4. So my example 4, is this an onto map? What do you guys think? By the way, what is the reduced row echelon form of the standard matrix for T? Trick question. It's its own reduced echelon form, isn't it? See that? Look at that. Like done, right? It's already reduced. Yay. What's the rank of that matrix? How many pivot columns? 2. Is this map onto? Yes, the output is R2. We have 2 pivot columns. We can reach everything in R2. It's an onto map. That's all there is to this. Now, sometimes we have a mapping which is both one-to-one and onto. That's called a bijection, right? A bijection of a linear map. It would be a linear map which has a linear inverse is a bijective linear map, which is also known as an isomorphism in the larger context. That kind of mapping we would need from like Rn to Rn, right? And we would need that the null space is 0 and that the rank is n. But you guys remember the rank nullity theorem? Like the dimension of the null space plus the dimension of the column space has to be equal to the number of columns. So like in the case that you are looking at a linear transformation from Rn to Rn, it's automatically onto if it's one-to-one and vice versa as it happens. So it gets a little bit simpler when we're looking at mappings from like Rn to Rn. But we'll talk. I'll do more examples of these another day. I wanted to get it on the plate for today so that you see it, but we'll do more. And like next class, you guys can ask me questions about what we did today, obviously. I don't think I have homework yet on some of the stuff I did today, but we will. Maybe I should give you like a take-home surprise attack mission about that, just to be fair. I don't think I should give it to you in class because it's not in the notes and, But anyway, I do have your test to get back to you, so let me do that. Anyway, thanks guys.